You know that feeling when you're staring at a massive spreadsheet, just hundreds of rows deep, and you feel completely, utterly overwhelmed? Yeah, you're definitely not alone. When we're confronted with raw, unstructured information, our brains naturally struggle to make any sense of it. Well, let's dive into this explainer and figure out how to uncover the hidden story inside that chaotic mountain of raw data. Today, we're essentially decoding the anatomy of data. Imagine you're a detective arriving at a scene, but instead of, normal clues, you just have a massive scattered pile of numbers. Numbers alone don't actually tell a story until you can map out their physical shape. Like if you just stare at rows and columns, you are completely missing the big picture. So our goal is to take that raw, messy information and condense it down so the true characteristics jump right out at us. We're taking the abstract and making it incredibly concrete. We call this specific process descriptive analysis. When researchers study this, they look at it as the foundational profile, the literal physical anatomy of the subjects we're looking at. It's essentially the study of distributions of a single variable, which gives us a crystal clear profile of a group. So whether we're looking at the overall size of tech companies, the efficiency of different work groups, or the highly specific buying preferences of everyday consumers, this analysis is exactly how we build our baseline understanding. Here's our roadmap for mapping this anatomy today. First, decoding it descriptive analysis. Second, measures of central tendency. Third, measuring data dispersion. Fourth, skewness and kurtosis. And finally, the story in the data. Okay, moving to section 1, decoding descriptive analysis. To really understand our tools, we absolutely have to know their limits, right? Data analysis is generally split into two major camps. Inferential analysis is what helps us make educated guesses, like taking a small sample of people and generalizing that to an entire country's population. It's all about testing hypotheses. But descriptive analysis, it does something entirely different. It's our tool for understanding the what is of a single variable right in front of us. It's not guessing what might be, it's summarizing the exact factual raw data we've actually collected. It's the absolutely crucial first step before any complex guessing can even begin. Let's jump into section 2, measures of central tendency. Once we actually have our data, the very first thing we want to know is where it naturally clusters. To find this, we rely on the big 3 measures of central tendency. First up, the mean, which is your standard arithmetic average, just adding everything up and dividing by the number of items. Second, the median. This is the exact middle item when you literally line every piece of data up from lowest to highest. And third, the mode, which is simply the single value that shows up the most frequently. Now, they're all considered statistical averages, but they each serve a totally distinct purpose depending on the real-world problem you're trying to solve. Let's look at a super practical example. Imagine a shoe manufacturer trying to figure out what sizes to produce for the upcoming year. They actually do not care about the mathematically average foot size. I mean, if the mean comes out to a size 8.3, that doesn't help them at all, right? Nobody buys a size 8.3 shoe. They need the mode. They need to know exactly which distinct whole shoe size has the maximum demand from the public. Once they find that mode, they know to make a significantly larger quantity of that exact size. It's just a completely different, business-driven way to look at the center of your data. All right, section 3, measuring a data dispersion. So here's the crazy plot twist. An average doesn't reveal the whole story. In fact, relying solely on an average can totally lie to you. Think about a neighborhood where 10 people live, and they each make $50,000 a year. The average is $50,000. Great. Now think of another neighborhood where 9 people have zero income, but 1 person is a literal billionaire. The average there looks fantastic, but the reality on the ground is completely different. A single representative figure is nice, but it can't show us how wildly the data scatters away from that center. We have to measure the dispersion. Are your data points huddled tightly right next to the average, or are they spread out over a massive, chaotic distance? We measure this scatter in 3 escalating steps. Step 1 is range, literally just the difference between the highest and lowest values. It's incredibly quick to find, but, rough and highly vulnerable to random outliers. Step 2 is mean deviation. Actually, scratch that. It's better because it looks at the average of differences from the mean. But mathematically, it just ignores minus signs. It treats a step backward exactly the same as a step forward, which honestly makes mathematicians super nervous. That brings us to step 3, standard deviation. This is the absolute gold standard in serious research. By squaring the deviations, it accounts for those negative signs totally legally within the math, giving us a precise, workable measure of the scatter that we can actually use for complex analysis down the line.
Moving right along to Section 4, Skewness and Kurtosis. This brings us to a researcher's absolute dream scenario, the perfectly symmetrical normal curve. In a perfect bell-shaped distribution, the mean, median, and mode are all exactly the same value. They sit right there in the absolute dead center, anchoring the entire data set. There's zero skewness. The data shows a perfect, harmonious balance on either side. It's beautiful, it's predictable, and it makes all your subsequent mathematical modeling incredibly straightforward. But let's be real. In the real world, data leans. When that beautiful balance gets thrown off to one side, we get what's called skewness. If the curve distorts and stretches its tail out to the right side, we have positive skewness. That just means a few abnormally high values are pulling the mean higher than the median and mode. Income data almost always looks exactly like this. If it distorts to the left, we have negative skewness, which drags the mean down below the median. Measuring this tells us the true physical posture of our data and warns us that our averages are being pulled in a specific direction.
And finally, we have kurtosis, which basically measures how flat-topped or sharply peaked the distribution is right in the middle. Just think of it as the humpedness of the data. If a curve is incredibly tall, narrow, and sharply peaked compared to a standard normal curve, we call it leptokurtic. It means the data is hyper-concentrated around the mean. If it's more flat and spread out, creating a sort of plateau, it's platykurtic. And if it happens to be that perfectly normal Goldilocks bell shape we just talked about, we call that mesokurtic. Yeah, they're definitely funny-sounding words, but they perfectly define the exact posture of your curve.
Which brings us to our final section, Section 5, the story in the data. So why does all this matter? Understanding these anatomical traits, the mean, the standard deviation, the skewness, the kurtosis, it is not just academic trivia to memorize for a test. Knowing the true shape of your data strictly dictates the exact statistical formulas and inferential tools you are actually allowed to use next. If you blindly assume your data is perfectly normal, but it's actually highly skewed to the right, your entire downstream analysis will literally be built on a mathematical illusion. You have to know the foundational shape first, before you start building your statistical house. And that brings us to the end of our roadmap. We now know that an average alone is just a single, isolated point, right? The true magic is in mapping the dispersion, the skewness, and the peaks to reveal the full, vibrant picture. Descriptive analysis takes the chaotic and makes it wonderfully clear. So, the very next time you are handed a massive mountain of raw data, ask yourself, are you going to just blindly trust the average, or will you uncover the true anatomy hiding inside? Thanks for joining me for this explainer, and keep looking for the story in the data.